Okay, I want you to close your eyes for a second. We are going to start today's deep dive by transporting ourselves way, way back in time.
Oh, setting a scene. I like it.
Yeah. Imagine you are standing on the swaying deck of this massive wooden ship. We're talking ancient maritime history here.
So maybe 14th or 15th century.
Exactly. And you are floating right in the middle of the Indian Ocean.
Okay.
The air is thick, it's humid, heavy with the smell of salt spray. And the cargo down below deck, we're talking peppercorns, cardamom, cinnamon.
So you're sailing from the Malabar coast of Kerala.
Right. Carrying what is, at the time, a literal fortune in spices.
That is a very high-stakes scenario.
Yeah.
I mean, it sounds romantic now, but back then, a trade route like that was incredibly dangerous.
Yeah, completely.
You're basically floating on a pile of money in a very fragile wooden tub.
Right. And the sun has just dipped below the horizon. Now, for the last 12 hours or so, you've been totally fine.
Because you have the sun.
Exactly. You've had the sun to keep your bearings. You know east is where it rose, west is where it's setting. But now it's night.
And in the ancient world, night navigation is a completely different beast.
Oh, I can't even imagine.
You are entirely dependent on the sky.
Yeah.
You don't have satellites. You don't have radio towers. You have the ceiling of the world, and that is it.
Right. You're looking for the pole star. You're tracing constellations. It's basically celestial GPS.
Yeah, if the sky is clear.
Right. And that brings us to the scenario that kept ancient sailors awake at night. The weather turns.
Oh, no.
Thick, heavy storm clouds roll in. The sky turns into this solid, impenetrable sheet of black.
The stars are gone.
The stars are gone. The moon is gone. You are floating on a pitch-black ocean with absolutely no visual references whatsoever.
That is a terrifying position to be in.
Right.
Because without a reference point, human directional sense completely collapses. We just drift. We sail in circles.
And in a storm, sailing in circles means...
It means you capsize or you smash into a reef. It is quite literally a life or death situation.
Yeah. So this is the exact scene set by a character named Reshma in the source material we're digging into today.
Right. She's writing a story.
Yeah, she's writing a story for her grandmother about this exact moment of panic. She puts her characters in this storm, and then she hits a writer's block.
Because she realizes she has no idea how they actually survived.
Exactly. She doesn't know how humanity unlocked the ability to navigate without actually seeing the world around them.
It's a really profound question when you think about it. It's this massive pivot point in history.
It really is.
It's the moment technology steps in to replace instinct. And the answer she finds, and really the core mission we are going to spend this deep dive unpacking, is the discovery of the inevitable force.
We are talking about the science of magnets.
Yes, we are.
And I know I can already hear you listening right now. You're thinking, magnets? You mean the little plastic fruit I used to stick my electric bill to the fridge?
It's so easy to dismiss them.
Yeah.
Because they are just so mundane to us now. They are toys, they are office supplies. But if you strip back the modern context, if you really look at what they do, the magnet is one of the most magical objects in the universe.
It completely defies our intuitive understanding of how physical objects should work.
It really does.
Yeah.
I mean, think about it deeply for a second. It is a rock that moves other rocks without touching them.
It's telekinesis.
It effectively is telekinesis. Action at a distance. That little black disc on your fridge is harnessing a fundamental force of physics.
Electromagnetism.
Exactly. Which is the exact same force that protects the Earth from solar winds. The same force that allows us to generate our electricity.
And the same force that guided those terrified sailors in the dark.
Precisely.
So, here is our mission for today's deep dive. We are going way beyond the fridge magnet.
Way beyond.
We are going to tear apart the physics and the history contained in these sources. We're going to figure out what a magnet actually is at an atomic level.
We're going to learn how to make one?
And how to destroy one, which, as we'll see, is surprisingly easy.
Very easy.
And we're going to solve some logic puzzles along the way that genuinely stump a lot of adults.
And we're going to look at the fish machine.
The fish machine. I am so excited about the fish machine. We will absolutely get there. But let's start at the very beginning. The origin story.
Let's do it.
Because magnets weren't invented in a lab, were they?
No, not at all.
We didn't just wake up one day and decide to invent magnetism.
Right. Long before we had factories or white coats or laboratories, we had geology. The origin story starts with a literal rock.
Okay.
Specifically, an iron ore called magnetite.
And in the history books, and definitely in our source material today, this is often referred to as lodestone.
Right, lodestone. And the name itself actually gives you a massive clue to its historical importance.
How so?
Well, lode comes from an Old English word meaning way or journey.
Oh, wow.
Yeah, so a lodestone is literally a waystone, a stone that leads you.
That is almost mythological, the stone that leads.
Doesn't it sound like something out of an epic fantasy novel?
Totally.
And it kind of felt that way to the ancients. Legend has it. And to be fair, there are many versions of this across different cultures, from Greece to ancient China.
Right.
But the core legend is that shepherds or travelers would be walking along and they'd notice their iron-tipped staffs or even the iron nails in their sandals getting stuck to these strange black rocks in the ground.
Just imagine the absolute confusion.
Oh, it would be terrifying. You put your walking stick down, and when you try to pick it up, the earth literally pulls back.
I would think it was possessed. I mean, if I'm a shepherd in 500 BC and the ground tries to steal my stick, that's spirits, that's ghosts.
You absolutely would assume it was magic. For centuries, people genuinely thought it was a soul trapped inside the stones.
A soul.
Yeah, a living force. But eventually, through observation, they realized two very specific things about these rocks.
Okay, what were they?
One, it attracts iron. Only iron, not wood, not leather. And two, and this is the absolute game changer, if you let a piece of this rock spin freely, it doesn't just stop randomly.
It points somewhere.
It stops pointing north every single time.
And that consistency is the key, right? If it did it once, it's a coincidence.
Exactly.
But if it does it 1,000 times, you've just discovered a law of nature.
Precisely. So those are natural magnets, the raw ore. That's what Rishma's sailors might have known about in the very earliest days of maritime navigation.
Right, but looking at the world around us today, like the magnets in your headphones or the strip on your refrigerator door, the latch on a pencil box, those aren't chunks of raw rock.
No, they look way too perfect for that. They're shiny, they're smooth, they're geometric.
Those are artificial magnets.
Right. At some point, humans realized that we could take the magic of the lodestone and we could actually transfer it.
We could copy the power.
We could induce that magnetic property into plain pieces of iron or steel. We essentially learned to manufacture the invisible force.
So we learned to mass produce it. And when you look at the source material, these artificial magnets seem to come in a very specific set of shapes. It's almost like a cast of characters.
It really is.
Yeah.
And form definitely follows function in magnetic engineering. In a typical physics lab or a school classroom kit, you'll see the classics. First up, the bar magnet.
The standard rectangular block.
Simple, effective, really good for studying the poles because they are as far apart from each other as possible.
Right, what else?
Then you have the cylindrical magnet, which just looks like a thick metal rod or a tube.
Right. And then, of course, the celebrity of the magnet world, the one that's in every single cartoon, the one Wile E. Coyote uses to try and catch the Roadrunner.
The horseshoe magnet, the classic U shape.
Now, why that shape, though? Is it purely aesthetic? Just because it looks cool?
Not at all. It's entirely about strength.
Oh, really?
Yeah. Think about a bar magnet. The two poles, the north and the south, are at complete opposite ends of the metal block.
Right.
So the magnetic field has to travel a really long way to the air to connect them.
Yeah.
But in a horseshoe magnet, you physically bend that bar so the two poles are sitting right next to each other.
Oh, so the gap is smaller.
Exactly. That concentrates all the magnetic field lines right in that tiny gap between the ends. It makes the grabbing power much, much stronger for picking things up.
That makes total sense. It's like using two hands to grab something instead of just one. You're focusing all the effort in one spot.
That is a brilliant analogy. And beyond those, you also have ring magnets and disc magnets, which we use in absolutely everything today, from audio speakers to electric motors.
The source material has this really fun section where it basically asks you to hunt for the hiding places of magnets in your own house.
Yes, the everyday encounters.
And it honestly made me look at my desk completely differently. I found one immediately in my pencil box. You know that really satisfying snap when you close a plastic case?
Oh, yeah. That's a magnet.
And the refrigerator door seal, that suction feeling when you pull it open isn't just a rubber gasket. There's a long, flexible magnetic strip hidden inside there.
Pin holders are another classic one mentioned in the text.
Oh, right, where you just drop a sewing pin towards the cup and it magically snaps right to the rim.
And the source mentions one that I think a lot of people forget about, the whiteboard duster in a school classroom.
Yes, the one that just sticks right to the board so the teacher doesn't lose it.
So we are completely surrounded by these artificial magnets. They are holding our daily lives together, quite literally.
But here is the first big filter we need to apply to our understanding today, because we all grow up saying this one phrase, Magnets stick to metal.
We do say that. I say it.
I say it all the time. Is it metal? Then the magnet will stick. That's the rule of thumb we all learn.
But that's a lie. Or at least it's a gross oversimplification of the physics.
I actually learned this the hard way trying to stick a heavy-duty magnet to a soda can.
Let me guess. It slid right off?
Way right down to the floor. And aluminum is definitely a metal. I checked the periodic table just to be sure.
You are correct. Aluminum is a metal. And this leads us to the concept of the material test.
Right.
The source text suggests basically walking around your environment with a strong magnet and just testing absolutely everything you can find.
Just tapping it against everything.
Exactly. And you very quickly realize that the physical world is divided into two very strict clubs, the magnetic and the non-magnetic.
So who actually gets past the bouncer for the magnetic club? Because it seems pretty exclusive.
Oh, it is extremely exclusive. The VIP, the one everyone knows, is iron.
Okay, iron is on the list.
Right. If an object contains iron like steel does, for example, it's in, the magnet grabs it.
But there are others, right?
Yes, there are two others that often get left out of normal conversation, but the notes specifically highlight them.
What are they?
Nickel and cobalt.
Iron, nickel, cobalt. The trinity of magnetism.
Effectively, yes. I mean, there are some complex rare earth elements too, but for your standard everyday household experience, if it's not iron, nickel, or cobalt, the magnet simply will not care about it.
So that means a solid gold ring.
Non-magnetic. The magnet won't touch it.
A silver spoon.
Non-magnetic.
Copper wire.
Non-magnetic.
That is wild. This is exactly why treasure hunters walking on the beach have to use electronic metal detectors, right? Those work on electrical conductivity and not just simple magnetism.
Exactly. If you tried to walk over a buried gold ring with just a giant magnet on a stick, you would walk right past a fortune.
That is tragic to think about.
Truly tragic.
But it's also a really useful way to test materials. The text calls this the material test for a reason. It forces you to stop looking at objects as just stuff.
Right.
You start looking at them as elemental compositions. It actually changes how you see the world around you.
It refines your view of the physical world. You stop seeing a quote-unquote silver spoon, and you start asking, well, is it actually silver? Or is it stainless steel?
Because the magnet will tell you the truth.
The magnet never lies.
Okay, so we know what sticks to a magnet. But let's zoom in on the magnet itself now. Because if you've ever played with iron filings, which, by the way, is one of the coolest visual experiments in any science class, you know that a magnet isn't just a uniform block of sticky power.
No, it's not. The stickiness or the magnetic force is not distributed evenly across the metal.
This is the anatomy of the magnet.
Yes. And the absolute best way to see this anatomy with your bare eyes is what we can call the iron filing revelation.
Walk us through this experiment. I can picture it in my head from middle school, but let's describe it clearly for the listener.
So imagine you take a clean sheet of white paper. You place a standard bar magnet flat on the table, and you put the paper directly over it.
Okay, so the magnet is hidden under the paper.
Right. Then you take a shaker full of iron filings, which are basically just tiny grains of iron dust.
Like a salt shaker.
Exactly like salting a steak. You sprinkle these filings evenly all over the top of the paper.
And then you tap it, right?
You tap the paper very gently.
Okay.
And the filings don't just pile up randomly like snow.
No, they move.
They dance. They shift around. And they magically arrange themselves into this incredibly intricate geometric pattern.
And the most obvious thing you see is that they aren't sticking to the middle of the bar magnet at all.
Hardly any filings stick to the middle. The dead center is almost completely bare. But at the two opposite ends,
It's crowded.
they are clustered incredibly thick. Spiky, bushy clusters of iron filings standing straight up like little hairs.
And these clusters are located at the poles.
Exactly. The North Pole and the South Pole. This visual proves that this is where the magnetic field lines are the most concentrated.
It's where the force is strongest?
Yes. You can almost think of the magnet as a pump for this invisible force, pushing it out violently from one end and pulling it back in at the other.
And here is where we get into something from the source material that I find genuinely mind-bending. The text calls this the unbreakable rule.
Oh yes, the absolute lack of monopoles.
Let's talk about this. Let's say I have a long bar magnet. North pole is on the left side, South pole is on the right side.
Okay, standard setup.
I take a metal saw and I cut that magnet perfectly down the middle. My human logic tells me, okay, I have physically separated them. I now have one piece of metal in my left hand that is just north and one piece in my right hand that is just south.
That sounds completely intuitive. It works that way with a loaf of bread. You cut the crust off, You have a piece with crust and a piece without. It works that way with almost everything in the physical world.
Right. If I cut a stick in half, I have two half sticks.
But magnets are weird.
Magnets are very weird. When you cut that magnet in half, the universe effectively hits copy and paste.
What do you mean?
The moment you slice through that metal, the newly cut end of the quote-unquote north piece instantly becomes South Pole.
Instantly.
Instantly. And the cut end of the south piece instantly becomes a brand new North Pole. You don't have two half magnets.
You have two smaller, completely whole magnets.
Yes. Each with their own brand new North and South Pole.
That is so wild to me. So what if I keep cutting? What if I take those two and I slice them into 100 pieces?
You get 100 tiny, perfect magnets.
Then I grind it into dust.
Every grain of dust has a north and a south. You can go all the way down to the atomic level, literally down to the spin of a single electron, and you still have a dipole, a north and a south. So you literally cannot have a front without a back.
You cannot have a top without a bottom. Nature simply refuses to let you isolate a magnetic pole. It is a fundamental duality of our universe.
So a monopole, a magnet with just a north pole and nothing else doesn't exist.
If you ever found a monopole in your garage, you would win the Nobel Prize immediately. You would rewrite modern physics.
I'll keep an eye out.
Please do.
It's almost philosophical, this idea of perfect duality. But practically speaking, this concept of poles north and south is what brings us right back to our terrified sailors in the storm.
It is the key to their survival.
Because having a rock that magically sticks to metal is a really cool party trick. But having a rock that tells you where you are on the planet, that is civilization-saving technology.
It is. And it relies entirely on the property direction.
So the core experiment here in the text is the freely suspended magnet.
Right. And anyone can do this at home. If you take a bar magnet and you tie a simple piece of sewing thread right around its exact center.
So it's balanced perfectly flat.
Balanced horizontally.
Yeah.
And you hold the string up and you give the magnet a little spin.
It spins, it slows down.
And eventually it stops. Now imagine you mark the exact direction it is pointing on the table below it.
Okay.
Now spin it again, agitate it, wait for it to stop again.
It will stop in the exact same position.
The exact same line. It's locked on to something invisible. It is not stopping randomly.
It is locked on. A freely suspended magnet always comes to rest in a north-south direction.
Always. The end that points towards the geographic north is called the north-seeking pole, or just the North Pole. And the other end is the south-seeking pole.
But why does it do that? I mean, why does a random piece of metal sitting in my living room care about geography? Does the magnet somehow know where Canada is?
Not quite. It's because it's not just a piece of metal in your living room. It's a small magnet sitting inside a much, much larger magnetic field.
The Earth.
The Earth itself. Our planet has a massive molten iron core that is constantly churning and swirling deep, deep underground.
Like a dynamo.
Exactly like a dynamo. That constant movement generates a massive magnetic field that surrounds our entire planet and extends out into space.
So for all intents and purposes, it's like there's a giant bar magnet buried deep inside the Earth.
Yes. So your little magnet hanging on a string is basically just trying to line up with the big boss.
It's falling in line.
It's physically aligning itself with the Earth's overriding magnetic field lines. And this is a key difference, and the text really highlights this as a major test between a true magnet and just a regular iron bar.
Right, because if I hang a regular iron crowbar from a string in my living room,
it will stop wherever friction or a slight breeze decides it should stop.
It might point east, it might point west-northwest.
It has absolutely no preference. It's completely agnostic to direction. Only a genuine magnet has a sense of direction.
And that profound sense of direction is what finally allowed humanity to confidently venture out into the open, featureless ocean.
It changed human history. Before the compass, you had to hug the coast. You stayed inside of land, or you sailed by the stars, which we established is risky.
Very risky.
With a compass, you can sail into the absolute void and still know exactly which way you are facing.
Now, speaking of the compass, the source material mentions an early device that I had actually never heard of before.
Let me guess. The Matsya Yantra.
The fish machine.
Yes.
I love the fish machine.
It sounds like something straight out of a steampunk novel. Tell me everything about the fish machine.
So this is a very early, incredibly clever form of the compass used by ancient Indian navigators.
Really?
And there were very similar devices used by ancient Chinese navigators as well.
Okay.
Instead of a thin little needle like we picture today, they took a small piece of magnetized iron and they literally beat it into the shape of a fish.
But why a fish? Is that just decorative?
Well, it was partially symbolism, sure, but it was largely about hydrodynamics.
Hydrodynamics for a compass. Yes, because of how they mounted it. They didn't balance it on a pin. They would fill a small vessel with oil.
Oil?
Oil is fantastic for this because it's viscous enough to keep the movement smooth.
Mm-hmm.
It stops the ironfish from wobbling around too wildly on a boat, but it's slippery enough to massively reduce friction.
Ah.
So they would take this ironfish and gently place it right on the surface of the oil.
So the ironfish floats.
It floats perfectly.
Hey.
And because it is physically suspended in liquid, it has almost zero mechanical friction holding it back from turning.
So even the incredibly weak magnetic force of the Earth is enough to move it.
Exactly. The Earth takes over, the fish slowly rotates in the bowl of oil, and the head of the fish reliably points north.
That is brilliant. It is so low-tech, but so incredibly high concept. The oil acts as a frictionless pivot. The fish is the indicator needle.
It is extremely elegant engineering for the time period. And really, when you get down to it, the modern compass is just a refined, dry version of the fish machine.
Right, we just swapped out the messy bowl of oil for a sharp little pin.
Exactly. A modern compass is literally just a lightweight magnetized needle, perfectly balanced on a very sharp pivot point. Again, entirely to minimize friction.
And it's usually sealed inside a little box with a transparent glass or plastic cover.
To keep the wind from blowing it around.
And usually one end of that spinning needle is painted bright red.
The north end, which is absolutely crucial.
Right, because imagine being in that storm we talked about earlier.
It's pitch black.
You look down at your unpainted compass needle, it's just a straight metal line.
If you don't know which end is pointing north and which end is pointing south, you have a literal 50-50 chance of sailing directly toward the deadly rocks instead of away from them.
You'd have to just guess. I have good news and bad news. We found land. The bad news is we hit it at full speed.
Exactly. The red paint removes the ambiguity. It literally saves lives.
Now, the text has this really hands-on activity where you can actually make your own compass. You can replicate this ancient, world-changing technology right on your kitchen table.
The DIY compass. This is an absolute must-try if you're listening. It completely demystifies the whole concept.
It proves that this isn't high-tech magic. It's just basic physics.
Exactly.
But first, you need a magnet. Well, specifically, you need a magnetized needle. And assuming I don't buy my sewing needles pre-magnetized from the factory,
which you probably don't.
I have to make one myself.
You do. You have to manufacture the force. And to do this, the text introduces the stroking method.
Which sounds very specific.
It is a technical term, I promise. The fundamental idea here is to artificially induce magnetism into a plain steel sewing needle by using an existing bar magnet.
Okay, sounds easy enough.
But there is a very strict, specific technique to it. You can't just rub the magnet back and forth on the needle like you're trying to scrub a coffee stain out of a shirt.
Scrubbing is bad.
Scrubbing is completely useless. If you scrub back and forth, you're constantly scrambling the microscopic magnetic domains inside the steel.
The domain?
Yeah, the tiny atomic magnets. You push them all one way, and then on the backstroke, you pull them right back the other way. You end up with an absolute mess. You confuse the metal.
So what is the proper technique then?
You need to be entirely unidirectional.
Unidirectional.
Yes. So place the sewing needle flat on the table. Take your bar magnet. Let's say you're using the North Pole end.
Right.
Place that pole down at the eye of the needle. Press firmly and drag it all the way along the length of the metal to the sharp point.
Down the shaft.
Right. Then, and this is the critical step, lift the magnet straight up into the air, arc it back through the air, place it back down at the eye, drag it to the point, lift, arc, repeat.
It's a completely circular motion. Touch, drag, lift, touch, drag, lift.
Exactly like petting a cat. You always pet a cat from head to tail. You don't rigorously rub the cat backwards unless you want to get severely scratched.
That is very good life advice. Let's not agitate the cat or the atomic domains.
Exactly. So you repeat this exact motion about 30 or 40 times.
Wow, that many times.
It takes a little persistence. What you are physically doing with each stroke is coaxing those billions of tiny atomic magnets inside the steel to all wake up and line up in the exact same direction.
Like a drill sergeant. Everyone look to the right. Everyone look to the right.
That is exactly what is happening at the atomic level. And once you've done your 40 strokes, you have successfully created a brand new magnet.
You can test it right away by seeing if it picks up a staple or a paperclip.
Yep. Now, to turn that raw magnet into a functional compass, you need to let it spin freely without friction.
So we need our own version of the oil from the fish machine.
Right. And the text suggests a brilliant modern shortcut. Taking a small, flat piece of cork or lightweight foam,
Okay.
you carefully stick your newly magnetized needle straight through the cork.
Like a skewer through a marshmallow.
Exactly. Then you gently float that cork in a small bowl of water.
Huh. The water is the zero friction pivot.
Yes. The cork keeps the heavy metal needle from sinking to the bottom, and the water allows the whole assembly to rotate effortlessly.
And if you've done the stroking method right, that little needle will slowly, magically swing
And it
around.
will point perfectly north.
You have just MacGyvered a functioning maritime navigation system out of household garbage.
You have. The only warning is to make sure the metal needle doesn't actually touch the water itself, or surface tension might drag it over and stick it to the side of the bowl.
The cork is your friend here. It's the hull of your tiny ship.
Exactly. Keep the hull floating free.
So we've covered attraction. We know magnets pull iron. We've covered direction. We know they point north. But there is another fundamental law of the jungle when it comes to magnets.
Yes.
And this explains how they treat each other when they are in the same room.
The laws of interaction. This is where the invisible force gets truly dynamic.
Yeah.
It's not just about a rock pulling a nail anymore. It's about two forces actively negotiating space.
We did the mental image of the iron filings earlier, but the text describes a completely different physical setup here to prove this interaction.
Right, the roller experiment.
It uses toy cars, or placing the magnet on round pencils, acting as makeshift rollers.
The roller experiment is so great because, once again, it reduces friction. Just like the compass oil or the floating cork.
Friction is the enemy of observing weak forces.
It really is. So imagine a bar magnet sitting horizontally across two parallel pencils.
So it can roll back and forth easily.
Right. Now you take a second bar magnet in your hand and you slowly bring it towards the magnet sitting on the rollers.
Okay, let's play this out. If I bring the north pole of the magnet in my hand towards the north pole of the magnet on the rollers, what happens?
The magnet on the rollers will run away from you.
It rolls backward.
It physically rolls away before you even touch it.
It's almost like it's afraid or disgusted. Just get away from me!
That is repulsion. The fundamental rule is, like poles repel. North violently pushes against north. South violently pushes against south.
And the force is surprisingly strong. If you've ever tried to force two really strong neodymium magnets together, north to north, it feels like there is a solid, squishy rubber ball wedged between them.
It does. It feels like physical resistance.
But there's absolutely nothing there, just empty air.
That's the magnetic field. You are literally feeling the invisible field lines compressing and fighting your muscles.
That is amazing. But, okay, what if I flip the magnet in my hand? What if I bring the south pole towards the north pole on the rollers?
Crash. They snap together instantly. The rule is, unlike poles attract,
It's the origin of the classic opposites attract cliché.
it is the absolute foundation of magnetic physics.